Hey guys, welcome back to Spatial Statistics. Last time we stopped on this slide where we developed the variogram cloud. We went through some important notation. If you haven't had a chance to watch previous video, it has an important notation that I'll be using basically from here on out. So the variogram cloud, on the y-axis, we are plotting the half the squared differences. And by the way, half the squared differences between all pairs of observations. That's where this prefix semi comes from. It's from the, on this y-axis. Half the squared differences between pairs of observations. And people use the word variogram and semi-variogram interchangeably. It's just dropping the half. It doesn't change the shape, right? It's just a constant. So if you see someone, or even you hear me say variogram or semi-variogram, it's the same thing. It's just where this half goes, whether the half is formally there or not. Okay, so on the y-axis, we have these half the squared differences, and this is basically tracking the dissimilarity in the data. As data become more and more dissimilar, our variogram grows. And then on the x-axis, we're tracking the distance, the Euclidean distance, and that's the dissimilarity in location. So just like we said last time, variogram clouds, when we plot all of our little data dissimilarities and location dissimilarities against one another, we get a cloud like this, and it's quite hard to read. It's hard to understand what's going on. So the strategy is we're going to divide our distances into bins and an arbitrary number of bins. Let's make that clear. And I think that's why people hate on variograms, is because based on several arbitrary decisions, the shape of the variogram and what it produces could look quite different. But here, I think I feel I'm using pretty reasonable options. I'm taking and finding distances up until 25 kilometers, because I know a couple of things about the city of London. If you go back to the maps we made on London, and you look at the scale of those maps, 25 kilometers covers quite a bit of the city. Again, we don't want to include those super observations that are too far away from each other, because the variogram becomes noisy. I'll show you what I'm talking about in just a second. So I'm using 25 kilometers or 25,000 meters as my cutoff, and I'm choosing arbitrarily to divide my 25,000 meters into 25 bins. So each bin is a 1 kilometer bin in which I will average my variogram cloud values. So I'm basically inside each bin, taking the average to produce these red dots, or the classic semi-variogram cloud values. If you look up the variogram formula, it looks just like this, but I want you to recognize here's the half, and then the n on the bottom, and this sum indicates that we're doing an average. There are issues with using an average when we have this many outliers, but this is what is done. I'm sure there may have been other developments around the variogram, but if you look at a lot of literature, the classic variogram is still being used. So how can we read it? Well, first of all, the code. The package that we'll be using is GStat. There's, in my experience, not a ton of packages to estimate variograms. The other big one is GOR. That's the other big one. Maybe there are some minor packages that have popped up here and there. Annoyingly, the code is pretty different. I like GStat because they make it easy to set the cutoff and reset the cutoff, and also change the width of your distance bins. So here I'm saying the cutoff is 25,000 meters, and I want to use 25 bins, so each one will be 1 kilometer big. Each distance bin will be 1 kilometer big. So here is the code to fit our variogram. Here is the code to make the default plot. Notice I'm using the gamma to denote my variogram value. This is the averaged variogram value from the previous slide, not the variogram cloud value. And here is my variogram. So typically we think there are 3 main features of our variogram: the nugget, the sill, and the range. So first things first, let's start with the nugget. The nugget is the value that the variogram approaches. The value that our variogram, I'll use H here to denote distances, that to match what I have here, H to denote distances. If you recall, the distance matrix can either be a D or an H. I don't know why, but these H's are just the distances, interpoint distances. So the nugget is the value that our variogram approaches as H becomes closer to 0. So as our distances get closer and closer to 0, our variogram is approaching what looks to be approximately 0.8. Approximately 0.8. This is a measure of non-spatial variability. Because we're looking at, we're not letting our points get far apart. In fact, we're trying to take our square differences as our points get closer and closer together. In fact, as H approaches 0, our points literally become the same point. So it is our estimate. Maybe that's a better word than measure. It's our estimate an estimate because we're using sample data. It's our estimate of non-spatial variability in the data. The sill. The sill, formally speaking, is the maximum value attained by the variogram. Now, clearly the maximum values here are a little bit above 1. And this is, by the way, our estimate. Let me erase some stuff. These slides were designed so that people can take notes by hand. I'm just not as nimble with my stylus. So the nugget is an estimate of non-spatial variance. The sill is an estimate of total variance. Nugget estimate of non-spatial variance. The sill is an estimate of total variance. And it is the maximum value attained by the variogram. However, in reality, we want to sort of adjust for noise. Each one of these data points on the left is comprised of different amounts of data, different amounts of pairs that we have pooled together. So we can't take this maximum value too seriously. We know that because these are z-scores, the variance is equal to 1. Total variance is equal to 1. Of that total variance, we know the non-spatial variance is about 0.8, right? It's the value that the variogram approaches as the distances get closer and closer to 0. As far as the sill goes, if you look at where 1 sort of crosses, let me take a different color. We sort of have to blur our eyes a little bit and say that, okay, what is the value that past a certain distance, our variogram is sort of oscillating randomly around? And that value seems to be about 1. I'll show you in about a sec that I can change the number of bins, and I can even sometimes change the cutoff, at least to be lower, not greater. And the variogram will still attain a maximum of approximately 1. So past a certain point, call it right there, there is no systematic variability. There's just random variability around 1. Yeah, so random variability around the sill. What helps us here is that we know we're dealing with a z-score. And so I'm just showing you that that's really what that variogram is picking out. The dots are picking off that 1, that total variance in the data. Okay. So I said past a certain point, the variogram no longer increases with distance, and instead the variogram remains stable as distance grows. So what is that point? That point appears to be right there. So a little bit less than 5 kilometers. And that is our range. It's the distance better. It's the distance at which the variogram attains its sill. And here it's, oh, I don't know, call it 4 kilometers, about 4 kilometers. Importantly, the range is the distance at which data are no longer correlated. So data points that are farther apart than 4 kilometers are no longer correlated. Data at which, it's a distance at which data not correlated. It's roughly speaking the zone of influence, if you will. If you average out over all the data points and you take a single data point, you take a buffer, a 4-kilometer buffer around that data point, you're saying there is correlation between that point and all data points in that 4-kilometer buffer on average, averaged across all 1,300 doctors in London. Okay, so to review, the nugget, non-spatial variance. The sill is total variance. The range is how far apart do we have to go until the data become uncorrelated, the distance at which correlation goes to 0, at least based on our variogram. So the nugget is actually a pretty useful little quantity. We said that the total variance is the sill, and that's 1. We also know this to be a fact, based on the fact that we're dealing with z-scores. The nugget is the non-spatial variance. By the way, the notation is usually tau squared. But again, annoyingly, this too varies from textbook to textbook and from package to package. You can look at it for the nugget effect or the nugget, but most often that I've seen, it's a tau squared, but don't hold me to that. People have changed that notation pretty frequently. So if the total variance is 1, and again, we're dealing with a z-score, and the non-spatial variance is 0.8, we can say that 80% of total variance in asthma prevalence is non-spatial. It's due to something other than the distance between observations. It's due to something other than dissimilarity in space. Demographics, the home environment, all of those will comprise that 80%. So percent nugget is basically here, right? So it's tau squared over sigma squared times 100% is percent nugget. Just very conveniently, our total variance in this case was 1. So we can pretty easily say that, well, with a nugget of 0.8, with a non-spatial variance of 0.8, 80% of our total variance is non-spatial. 20% is spatial. I claim that is still non-trivial. So then 20% is due to something spatial. It's due to the distance between observations and whatever is measured by that, the dissimilarity in space. So the last thing about reading a variogram is perhaps the toughest. And if you're already listening to me and you're saying, boy, we're really reading tea leaves here. Yeah, variograms can be tough to read. I picked a case with a lot of data and a pretty stable sill. And also we know the answer. We know that sigma squared, the total variance, should be 1. So that really helps us out. That really helps us pick out where that range occurs. Right? I know the variance is 1, so that allows me to, if this line was vertical, to just pick out that range, the distance at which data no longer are correlated, and call it, oh, I don't know, 4 kilometers. In the case that I don't know what the total variance is, it's a lot tougher to read the variograms. And we'll have plenty of practice, and I'll show you some messy examples as well. Okay, the shape of the variogram. So this has to do with the fact that we're actually still not doing any modeling. When you're thinking of imposing structure on that correlation, the shape of the variogram tells us what kind of structure might be appropriate. So this helps impose structure on the correlation via a model. I'm waving my arms for now. I hope we'll spend a lot more time on this in the second part of this unit. So, long story short, what you're looking for is linear behavior at the origin, linear versus curvilinear. At a distance of about 0. Linear versus curvilinear behavior at a distance of about 0. So yes, we are talking about these, what turns out to be 5 data points. And even these 5 or 6, and I'm not even talking about these. I'm talking about maybe these guys right here. And remember that the number of bins is arbitrary. And so the more bins we have, the better I can assess the behavior of our variogram near the origin, and that can help me pick an appropriate model to impose structure on our correlation. But if I have too many bins, I'm going to be averaging data from fewer and fewer pairs of observations, and I will introduce more and more noise. So there's a trade-off there, and that trade-off needs to happen very smoothly. And you know, it takes a little bit of experience to make appropriate decisions. So with these data right here, as I see it here, I would call this linear behavior. Linear near the origin. But flip to this slide. Look at this rightmost panel here. What I did was I used twice as many bins. Same cutoff, but twice as many bins. So the bins are 1/2 kilometer in size, 1/2 kilometer bins. Here we have 1 kilometer bins. So look, I have given myself an extra dot near the origin. Could I not say that, oh, I don't know. Could I not see if I blur my eyes enough that it goes like this, the variogram? I don't know. Could it go like this, the variogram, which I'm trying to make a linear shape? In the end, could be linear or non-linear. So we're frustrated. We don't know. Well, when we get to modeling, the modeling stages of this unit, we can fit the linear, fit the nonlinear, and do something like compare our information criteria, compare our predictive mean squared error. But right now, we're just in this variogram world, and I'm pointing out all the ways in which it's hard to read variograms. In this case, though, we see that, you know, the sill, it's still around 1, where this variogram with the smaller bins levels off is still around 1. It looks like the nugget, however, has creeped up a little bit to something above 0.8. So with more bins, my percent nugget, I don't know, 0.85, 0.82. I'm no longer convinced it's 0.8. So the amount of spatial variability has dropped when we are getting a more precise reading near the origin with 50 bins. To be clear, the left panel and the right panel are both okay. I would go and put either one of those in a publication. I think I just picked 25 because frankly, I think it looks better. I think the 50 bin one is a little bit noisy for me. That is an arbitrary call. That is a judgment call. The one that does not look good is the middle panel. Remember, our sill, estimate of total variance, the maximum value attained by the variogram. We're looking for our variogram to reach that sill and sort of stay there, right? Reach the sill and sort of stay there. This variogram has sort of this kind of shape. And look at this noise right here. Because when we are out there by 50 kilometers, the number of pairs goes to 0 or goes to 1, not 0, 1. The minimum number of pairs is 1. We don't want to be estimating our total variance based on just one pair of observations. There's just a square difference between two random observations. So we really want our variogram to have that classic, what I'm telling you is a classic sort of up and flat shape. We don't want things that blow up this way. We don't want things that kind of curve this way. That means that we have either gone out too far or we have missed a trend in the data. Let me make 2 more relatively quick comments about variograms, and then I want to flip to R and show you a little bit. So just kind of run through a little bit of a demo. Okay. We've been thus far using eastings and northings because we like meters. We don't like decimal degrees. I just want to show you what happens if you do use decimal degrees. Remember, we're operating inside the city of London. That is a relatively small area. So why do you think the impact on this variogram was relatively minimal when we have flipped from meters to decimal degrees? London comprises, I like this word today for some reason, a relatively small region. On the scale of the world, London is quite small, and so any kind of distortion that is introduced by using latitudes and longitudes and not projecting them into meters is minimal. However, you know, the variogram looks slightly different, especially its behavior near the origin, but recognize, right, the 3 features of our variogram: nugget, range, and sill. All right, the nugget. It's the value of the variogram that the variogram is approaching as our distances go to 0. So, I don't know, around 0.8. That's consistent with what we saw when we used eastings and northings. Next, the sill. The maximum value attained by our variogram. But we know it's not really the maximum. It goes up and then kind of hovers around a certain value. And so if I kind of extend this out, we see that the sill is pretty clearly 1. That's the total variance. Then the distance at which our variogram reaches our sill is the range. And again, the range is the distance at which 2 points become independent on average. So that range is 0.05 decimal degrees. Because each bin is 0.01 degrees and 0.01 degrees is approximately 1 kilometer, this is approximately 5 kilometers. So there's a great deal of agreement between using eastings and northings and using lat long distances. And the reason why, London is a relatively small region. If you did this for the entire North America, you would probably see some differences. One more sort of comment before we flip to R. You might be reading or seeing a paper or have someone tell you, oh, you're learning about variograms, let me show you a variogram. I know it happens all the time. But sometimes people say, you know, I'm not going to blur my eyes. I'm just going to fit a line through my points. We're allowed to do that. We have a well-known method for fitting lines through points using OLS regression. So a few things. Number one, this is not a straight line, right? So actually, the line is a variogram model. not a straight line. And so we're going to talk about these later when we're talking about the models for spatial correlation. But the other issue is these dots, the blue dots, they're not really data. Remember that each dot is an average of squared differences. It's not an observation. It's an average of squared differences. Not observed data. So we can definitely use this type of line fitting as a computational tool, as an exploratory tool. For example, when I fit my line through, my nugget effect is definitely far closer to 0.8 than it is to 0.85. And my sill nicely ends up to be 1. My range is, just a little bit, maybe less than 5 kilometers. Just don't take that fitted line too seriously. Don't start doing R squareds and such on it. The other issue, not every one of those points contains the same amount of data. The points closer to the origin have more pairs. Points that are farther away have less pairs. So there needs to be some kind of a weighting approach, and that's really what's done when you fit these kinds of lines. We'll talk a little bit more about this in the next part of this unit. All right, allow me to flip to R and kind of demonstrate a couple of things about variograms as they apply to our asthma example. So a reminder, here is London, here are the GPs. Here is z-scored prevalence. This is not a percent prevalence. It's not the percentage of the patients that have asthma. This is a z-score. You can see there are clearly negative numbers. So negative numbers indicate that the asthma prevalence is below the average. Positive z-scores indicate asthma prevalence is above the average. So this nicely, I think, points out there's this cluster of green values where the prevalence of asthma is quite low. This is the darkest green color. So there is very little, comparatively, asthma in this area than the rest of London. Now, maybe a little bit more here than the rest of London. So, remember, when we first started this class, I said, think about modeling patterns. What are some patterns that you're seeing? I think one prominent feature is the river Thames. It's right here. Here's the river. The elevation at the river, as you might imagine, is low. Then the rest of the city is kind of, well, above the river. It's, there are some hills, some hilly areas. So what I'm building towards is that I actually have in my London data the elevation, the altitude of that office, that doctor's office in meters. 9 meters, 5 meters, here is a 13-meter elevation. I also have the region name that the doctor belongs to. So it's called STP name, Northeast London, North Central London, Southeast London, so on and so forth. That's a bigger region than these borough divisions, right? So regions, there are 5 of them. They combine boroughs together. So it's natural for us to begin the modeling process by saying, okay, well, can't I use all the available information to me? Must I use spatial statistics? Good question. So here are 2 models, and I just wanted to show you that I didn't just jump straight in to this model. I built it to demonstrate sort of good behavior, if you will. But this is nothing more than just a linear model. Here is my z-score prevalence as my outcome variable. Here is my altitude, and nothing is linear, so I'm including a squared altitude for a quadratic effect. And I'm including the categorical variable for region. Again, not borough, but region. There are 5 regions. So when I fit this, and I look, I see that, hey, altitude, the test statistics are all large in their absolute value. The p-values are almost 0 for altitude. So altitude matters. How much? Well, that's the other question. The entire model only explains, oh, I don't know, the adjusted R-squared is barely about 5%. The unadjusted R-squared is just over 5%. So although these 2 variables are statistically significant, they explain very, very little variability in asthma prevalence. But nothing stops us from looking at our variograms with covariates in the variogram. So, to be clear, if we go back here, my Z prevalence tilde 1 means I have no covariance. I can only do that when I have a constant mean. And with a Z-score, I do have a constant mean. When I use covariates like this, what I'm actually performing my variogram analysis on are the residuals, are the prediction errors. And so down here, I may have the same cutoffs. I will start with the no covariate case, right? We have no covariates here. And then I introduce first just the altitude and the squared altitude for a quadratic, and then both altitude and region. And then when I put it inside this variogram function, I'm actually performing my variography, my variogram analysis, not on Y, but on epsilon. Let me write it right here. With covariates, both quantitative and categorical, interactions, anything you want. Variogram analysis is done on the residuals. Call it epsilon, SI, epsilon, SJ, right? Half the square difference this works because our residuals have mean 0, constant mean 0, and are assumed to have a constant variance. So that helps us meet that second order stationarity assumption. Okay, let's take a look at what happens. I keep my cutoffs and number of bins the same. I'm still using 25 1 kilometer distance bins. I fit 3 variograms, or I don't fit the variograms, I compute the variograms based on the residuals from 3 models. One model has just the intercept, no covariates. The second model has intercept and altitude squared. The third model has, in addition to all that, the categorical region name. I will fit this. And now put them side by side. By the way, to put them side by side, let me make the plot first and I'll show you. I need to use the generic function, a generic plotting function, not the GStat specific plotting function. And it might be interesting to look at what is contained inside this variogram v-omni object. NP is the number of pairs. You see that it actually peaks around, what's that, around 13 to 14 kilometer distance. Then it starts to diminish again. If I use a cutoff of 50,000 with, say, 50 different bins, so I want to keep my bins at 1 kilometer wide, but my cutoff increases to 50, and now I remake the variogram. Look at this object. Look, when we are looking at 1 kilometer bins that are 50 kilometers apart, this is 49,400 meters apart, I'm down to 85 bins. So that is why what we want to do is we want to cut it off well before we get into this noisy number of pairs world. And that happens, as I said, rule of thumb is about half to 0.75 of the total observed distance. Okay. Let me refit my variograms. So switch this back to 25, switch this to 25, refit, and put them side by side. Just for the sake of completeness, I will not remember what I ran and when. So here we are. Here are my 3 variograms. You will notice there is not a ton of difference in our variogram when we look at it without any covariates and with some covariates. And this is important because this means that covariates did not fully explain the spatial pattern, the spatial clustering. Whether it is without any covariates or with all kinds of covariates, there is a short, relatively short range spatial process still present. A short range. I think this line is at, well, I can just flip back and see. That line is at 3 kilometers. That line is at 3 kilometers. There is still a 3 kilometer spatial process present. Okay? If, on the other hand, when I included covariates and recomputed the variogram, if my variogram would look like, I wonder if I can clear them all off. Clear. Oops. If, on the other hand, I started to compare my variogram with no covariates of any kind to a variogram with all kinds of covariates, and what I would get was actually something that looked like this. Now, clearly this is a little too pretty, but now the range is approximately 0. And there is no longer residual correlation in the data. So we could say if what you saw were these red dots, you could say that, yes, when I look at my data with no covariates, I detect some spatial correlation. But when I include altitude and region in there, that explains the spatial patterns in the data. That accounts for the clustering to where what is left over is now noise. Okay? Okay. The other thing I wanted to show you guys is what about that second order stationarity? What about that second order stationarity? That's when we assume that the nature of the spatial process does not vary with location. That means that the variance is constant spatially, the mean is constant spatially, and the nature of the spatial correlation itself is constant spatially. How can we check that? Admittedly, it's hard. It's hard, I think, when you talk to anyone. We have enough data here that we can do something about it. And what I'm trying to do is actually compute a variogram by region. So I'm going to compute 5 different variograms, one in the Northeast, one in the North Central, Northwest, Southwest, etc. So there's a bit of code, of course. Notice that my cutoff has to be smaller because I'm no longer looking at the city as a whole, I'm looking at a sub-region of the city. So after some trial and error, I picked 8-kilometer cutoffs, and after some trial and error, I picked 10 bins. So that means each bin is 0.8 kilometers wide, each distance bin, where I'm averaging my variogram cloud. Right here on line 142, I have code that takes a subset of the data set and only takes Northeast London. Down here, I make a second variogram where I take North Central London, so on and so forth until I get 5 different variograms. The other thing that you should see is I'm using no covariates because I want to examine as quote unquote pure a spatial correlation as possible and how that varies by region. All right, perform my estimation. These things run very quickly. And then plot side by side. And now, well, we get to look at and compare 5 different variograms. So first of all, I just made this figure large. In general, when you have multiple panels in a figure, it's better to make them relatively narrow and tall to see the patterns better in the data. So let me do that. Let me try and make these panels narrow and tall a little bit more. You know, you get you watching me struggle with it today. And all right, there we are. Here are my variograms with no covariates, 1 per sub-region of the city. Now, they do look different. Specifically, notice that the sill is different. The sill in Northwest London is 1.5. The sill in Northeast London is not even 1. Before, I was looking at London overall. What about the Nugget and the range? Well, here in North Central London, we have sort of a well-behaved variogram, and you can't take it too seriously because now we've taken 1,300 doctors and we've reduced the amount of data that we have. But yeah, you know, maybe we do have something there. We definitely don't have much in the Northeast, and we definitely don't have much, I think, in the Northwest. But in North Central, Southeast, and Southwest London, I see some evidence of spatial correlation. Now, is this conclusive evidence that second order stationarity is broken? I don't think this is conclusive. I don't think that, first of all, I'm not aware of like a test that will produce a p-value. If you're thinking of doing some kind of an ANOVA to compare 5 variograms, you have to keep in mind that there's a different amount of data in each one, and you're not analyzing observations, you're analyzing average square differences between residuals. So it's hard to be too quantitative when we're looking at second order stationarity. The second comment is, this is just a convenient way of grouping data. Couldn't we look at distance bins, altitude bins? So we did a 1 variogram for low, you know, for the doctor's offices that were at low elevation and another variogram at high elevation? Yes, we could. Couldn't we do that and by region? Sure. But at that point, you're cutting your entire data set into smaller and smaller pieces, and your variograms behave worse and worse. In general, I think that there might be some violation of that second order stationarity, but I don't think it's nearly strong enough to write home about. So let's actually stop right here. We're doing okay on time. Next time, we will go through some extensions and reformulations of our variogram. We will talk about just kind of flipping the variogram on its head and looking at covariances instead. We will start to also introduce direction into our variograms, where instead of being omnidirectional, pretty soon our variograms will become directional. So a few more slides, mostly pictures next time. We will call it quits for this week. We have another bit of new material next Tuesday, an activity next Thursday. Thank you guys so much for your attention. Have a great weekend.